In this video, we're going to explore the Nernst equation a little bit further to find the potential of a voltaic cell that's no longer at standard state. Let's use our normal zinc solid plus copper 2 plus aqueous going to zinc 2 plus aqueous plus copper solid. So our voltaic cell has a solution, has the zinc bar in it. It's going to connect to some device, it's going to go over to the other side, it's going to have a copper bar in it. It's going to have stuff in solution and salt bridge. Well, the potentials we normally calculate are at standard states. 298 Kelvin, 1 molar solutions. If we had gaseous components, 1 atmosphere pressure. In this case, we have solutions that are assumed to be 1 molar. In previous videos, we've calculated out that the E0 cell for this is 1.10 volts for our copper zinc system. So we can have our E cell here. We're going to need to know Q. And so Q is going to equal our products over a reactance, which is zinc 2 plus, copper solid, over our reactance, zinc solid, copper 2 plus. Well, the solids cancel out. Their concentrations don't change. So they're not part of an equilibrium expression. Our solutions, however, are. And so our Q is going to be our zinc concentration over our copper concentration. If you want to think about this relation for a minute, remember that equilibrium expressions are very large for electron transfers between materials. Copper really wants that electron, and so K in the end is going to be really large, which means we're going to have very little copper 2 plus left, so very small number in bottom, and we're going to have comparatively way more zinc 2 plus. So by the time we reach equilibrium, the top should be very large, the bottom should be very small. And at that point, our Q should equal our K value. If we'd had these flipped and copper on top, well, that top would go to almost to 0 by the end, and that would give us a very small K, but we expect a large one. So while it isn't necessarily super obvious why this is a relation, other than kind of writing products over reactants, we can think about it for a minute to see, oh yeah, that is why the zinc solution is on top. That's what we have in the end. We make way more zinc plus 2. Our reactant was a bunch of copper 2 plus that we had to get rid of. So if we have a cell that's not at standard states, let's say that we have 0.1 molar copper 2 plus, but we have 0.75 molar zinc 2 plus. So I have a system that just has way more zinc than copper. Instead of both being 1 molar, we're short on both, but we're far shorter on the copper. What would be the potential of this cell? Well, our E cell for our actual system is going to be equal to the 1.10 volts minus 0.0592 volts, 2 electrons in the formula, log of 0.75 over 0.1, which is 0.87506, times that by the front, comes out at 0.0259. So 1.10 volts minus 0.0259 gives us an actual potential of 1.074 volts. Having 7.5 times more zinc ions than copper did slightly modify our voltage. While electrons still tend to flow towards the copper, there's a little backflow, a little weakening of our potential, as more zincs are impacting, trying to pull electrons more often than the copper, and causing a little bit change. We can even use this to figure out at what relative amounts our voltage will change to a certain amount. If a device didn't work past, say, 0.9 volts, and you were using 1.1 volt zinc copper batteries, now what relative ratio of reactants and products would your battery decrease to the point it wouldn't be able to run your device anymore? Well, 1.10 volts is the standard potential. We're going to lose from that 0.0592 volts divided by 2 log of that ratio. what ratio do we have to get our two materials down to? Calculate across, minus 1.10 volts. At minus 0.2 volts, being equal to minus 0.0597 volts over 2 log of our ratio of zinc over copper. Adjust again, our log of that ratio. We'll divide 0.0597 divided by 2 across. So 0.2 divided by 0.02985. 6.70 must equal the log of x. Take 10 to both sides. 5.01 times 10 to the 6. So about 5 million times different. So one of them at 1 molar, the other at half a micromolar. That's a pretty significant difference before you're down to 0.9 volts. At that point, you've transferred the vast majority of the electrons. There's almost none of the other material left by comparison. And so you don't really have to worry about this dropping below the minimum voltage necessary to run whatever device that we were theoretically looking for here. It is possible to change our voltage here by 0.2 out of original 1.1, so just about 20% voltage change. But it took us having our concentrations change to the point of being over 1 million times different from each other. And so as the copper in the solution would get used up and the zinc would get created, we'd get down to the point of having almost used all the copper in solution before we got below this point. Very few electrons would have been left to transfer that we miss out on.